Now let's talk about the second question. How can we calculate the R-square value? This is required and very important to know. Before we answer this question, we need to go back to take a look at the values we get. We need to understand the three symbols in a mathematical way. We have y, y bar, and y hat. What y represents? Y represents the real values of the dependent factor. What about y bar? Y bar is the mean of the real values of the dependent factor. For instance, when we ask the user how long they spend on our mobile app every week, they will give us the real time they spend on the mobile app. When we get those data, we can calculate the y bar, the mean time they spend on the mobile app right away. So this is what y bar represents. What about the y hat? Y hat is the estimated values of the dependent factor according to our equation. Based on y, y bar, and y hat, we can calculate several factors to measure the performance of the equation we got from the Excel software. The first factor is called the total sum of squares, or SST. This slide shows you how to calculate SST. The calculation is out of the scope of this class, but we have to understand what SST represents. Actually, SST measures how the real observations of the dependent factor changes around the mean. And then we have the sum of squares due to regression, SSR. What does SSR measure? It measures how the estimated value of dependent factor changes around the mean. Now let's think about this. If our estimation is perfect, the equation we got from the software can precisely predict the future. Then SSR should be as same as SST, right? That means your estimated value is as same as the truth, but we can't. Because when we make the estimation, we will inevitably incur some errors. As you can see in the Excel software, we calculated the total of the residual squares. It is 8.02. We call this total of the residual squares the sum of squares due to error. As we discussed in the previous lecture, we want the SSE to be as small as possible in order to reduce the influence of errors on our estimation. When SSE is becoming smaller, the percentage of SSR taken in SST will become larger because these three factors have the relationship as shown on this slide. SST equals to SSR plus SSE. I uploaded a document to eCollege to show you how this relationship is built. For now, we need to remember that when the influence of errors is becoming smaller, our estimated equation can explain the truth more. So this is what this equation shows to us. According to SSR and SST, we developed the R-square. R-square equals to SSR over SST. R-square represents how much the estimated equation or the regression model we got from the software can explain the real relationship between the independent factor and the dependent factor. The values of R-square always range from 0 to 1. The higher, the better. The higher the R-square is, the more we can use the estimated equation to explain how X factor influences the Y factor, how the independent factor influences the dependent factor. Now we know how R-square is calculated, but do we have to calculate SSR and SST? We don't have to. In the data analysis report, we can find the values for SSR and SST right away. In the report, you will find the SS column. The value for SSR is in SS for regression. The value for SST is in SS for total. Now you get SSR is 15.87, SST is 23.9. Let's use these two values to calculate R-squared. In cell D5, I want to type in equal sign and then click on cell C12 / and then click on cell C14 and then press enter button on your keyboard. We get 0.664. Is this as same as the R-squared given by the software? It is. And this shows you how you calculate the R-squared value. Now let's talk about the third question. What is the managerial implication of this linear model of this equation we got from the software? We got y hat equals to 1.2739 plus 0.0678 times x. What does this mean to business manager? From this equation, we can find that there is a positive relationship between the independent factor and the dependent factor, because the coefficient of the independent factor is a positive number. This shows that the higher the user's yearly incomes are, the more time they will spend on our mobile app. As a business manager, this provides several implications when you make your marketing strategy. For instance, you want to focus on the user group with higher yearly incomes. For the users with lower yearly incomes, you probably want to educate them, make them more health conscious in order to use your mobile app more. However, the equation is estimated according to only 10 users. Can we predict that the population has the same relationship? Don't forget, when we get the relationship, when we get the values of b sub 0 and b sub 1, we made a very subjective estimation. What is it? Let me show you again. Click on Data, and then click Data Analysis, and then choose Regression, and then click OK. For the Y input, we choose C1 to C11. For the X factor, we choose B1 to B11. And then we check the box before labels, right? Also, we want to check the box before confidence level. As I showed you in the previous lecture, we said the confidence level is a very subjective number. You can use any number between 0 to 100 to represent how sure you are about the relationship between X and Y. Usually we will use 95% and 99%. So in this case, let's use 95%. This means we are 95% sure about the relationship between X and Y. What about the rest of the 5%? That is called the region of errors. That means we are not sure, we are 5% not sure the relationship between the X factor and Y factor. Another name for that 5% is called the level of significance. So we have a 5% level of significance in the estimation. This 5% level of significance set up a bar for us to say if we can use the model from a sample to predict the model of the population. Now let's come back to the model from the sample. We need to check 3 factors in the model from the sample. First, we want to test the overall regression relationship. We want to see how strong this estimated equation is. Second, we want to test the individual regression parameters such as b sub 0 and b sub 1. We want to see how strong these two values can predict the dependent factor. Third, we want to test if the residuals are independently and randomly distributed around the value of 0. Let's see these three factors one by one. First, we want to test the overall regression relationship. We use the f-test to show how strong the model from the sample is. This slide shows you how to calculate the f-value. Fortunately, we don't have to calculate the f-value manually. In the data analysis report, you can find the f-value right away in the report. It's in the middle of this report. We got the f-value as 15.814. Corresponding to the f-value, we can get the significance of f. The significance of f represents how likely this equation will actually make a mistake when it estimates the relationship between the x factor and the y factor. We got the significance of f as 0.00408. It is a very small number, right? Let's change the number to a percentage. It's so small that the software cannot find any value for it, so it shows 0%. If we increase the accuracy of decimal point, we still get a very small number, 0.41%. This means there is only a 0.41% chance for the estimated equation to actually make a mistake. When we estimate this equation, we thought we have 5% chance to make a mistake, but the actual result has only 0.41% chance of making a mistake. This is better than we thought. We can then make the conclusion that the overall regression relationship is strong in this model. Now you need to remember, if you want to say the overall regression relationship is strong, the value for the significance of f must be smaller than the level of significance. What if the value of significance of f is greater than the level of significance? Let's say in F12 we get 10% now. It is greater than the 5% level of significance. What does that imply to us? That means if you want to use the model from the sample to represent the model of the population, it's suspicious because the real model is more likely to make a mistake than we thought. If that is the case, we have to draw a new sample and then find a new model, and then we will see if the significance of f value is less than the level of significance. If it's still greater than the level of significance, we can repeat the same process. Draw a new sample until the significance of f value is less than the level of significance. This is how we perform the f-test. Remember, we can only see the overall regression relationship is strong if the significance of f value is less than the level of significance. Next, we want to test how each individual parameter in the model influence the dependent factor. What are the individual parameters in our model? They are b sub 0 and b sub 1. From the linear regression model, we get the value of b sub 0 and b sub 1, but we haven't tested how influential they are on the change of dependent factor yet. This is the second step we want to check. We want to test how each individual parameter influence the dependent factor. We use the t-test to check the influence of each parameter on the dependent factor. And this slide shows you how to perform the t-test. Do we have to calculate the t-value manually? We don't have to. The Excel software has offered the t-values for the value of b sub 0 and b sub 1. Once you look at the data analysis report, at the bottom you will find the t-stat column. These are the t-values for b sub 0 and b sub 1 respectively. So now we get the t-value. How can we make the conclusion that b sub 0 is influential to the change of the dependent factor, b sub 1 is influential to the change of the dependent factor? Corresponding to the t-value, we have a p-value next to it. What is p-value? Similar to the significance of f-value, p-value represents the real chance for each parameter to make a mistake when we use that parameter to predict the change of the dependent factor. We can only say the parameter is influential to the change of the dependent factor if the parameter's p-value is less than the level of significance. Let's see some example. So the p-value for b sub 0 is 0.389. Now let's change it to a percentage. This means the p-value for b sub 0 is 39%. Our level of significance, the standard bar, is only 5%. However, if we use b sub 0 to explain the change of the dependent factor, the real chance for b sub 0 to make an error is 39%. This is way worse than we thought, right? So we cannot say b sub 0 is an influential factor on the change of the dependent variable y, because the real chance for it to make a mistake is way too high. Now let's see the p-value for b sub 1. Again, we get a very small number, 0.004. Very close to 0, right? Let's change it to a percentage. Let's increase the accuracy of decimal points. As you can see, the chance for b sub 1 to make a mistake when it explains the change of dependent factor is only 0.41%. It's way smaller than the standard bar 5%. And then we can say b sub 1 is an influential factor to the change of the dependent variable y. We call b sub 1 a significantly influential factor. Obviously, b sub 0 is not a significantly influential factor. This is how you perform the test for each parameter in the model. Next, we want to test if the residuals are independently and randomly distributed around the value of 0. We need a function from Excel called a residual plot to see if the residuals are independently and randomly distributed around the value of 0. Let me show you how to get the residual plot. Let's go back to Excel and then go to the data set. Click on data and then click data analysis. And then choose regression. And then click OK. Again, we need to choose the range for the y factor. It will be the time the user spent on our mobile app. The x factor, it will be the user's yearly incomes. We want to check the box before labels, check the box before confidence level, and make sure the confidence level for this case is 95%. And then check new worksheet apply. And then check the box before residual plots. And then click OK. Now we get the data analysis report as same as the one we got before on the left. But on the right, we have a new chart. This chart is called the residual plot. Now you need to notice that the blue dots on this chart do not represent the user's responses to our survey anymore. They represent residuals. We have two sections in the residual plot. The section above, as you can see, the section above, this represents the positive part of the residuals. All the residuals in the section above are positive numbers. All the residuals in the area below are negative numbers. And then in the middle, we have a very long line, right? If you look at the left side, the value of this line represents 0. This means the 0 line. We want to make sure that all residuals are randomly distributed around the 0 line. Looks like the blue dots randomly distributed around the 0 line, right? Second, we want to make sure that all residuals are independently distributed around this 0 line. What does this mean? This means the residuals are not influenced by the external factors. As you can see, on the 0 line, we have some values, 0, 20, 40, 60, 80. What are these numbers? These are the increase of the dependent factor, right? We want to check if the residuals has some certain patterns or trend when the dependent factor increases. Looks like there is no particular trend among the residuals. This means when the dependent factor increases, the residuals still randomly distributed around the 0 line. They are not influenced by the increase of the dependent factor. This is very good. Now let's see some bad residual plot. Here are some examples of problematic residual plots. Let's see residual plot A. The residuals are distributed around the 0 line. However, when the independent factor increases, the residual shows the trends. Let me draw the trends. As you can see, there is a trend, a scattering trend among residuals. This is problematic. We cannot see residuals are randomly and independently distributed around the 0 line. They are influenced by the increase of the X factor. Let's see the second residual plot. Again, this shows some trend. When the X factor increases, the residual plot shows the trends. So they are also influenced by the change of the independent factor X. We cannot see the residuals are independently distributed around 0. What about the third one? The third residual plot. They don't show some trend. However, they are not randomly distributed around the 0 line, because the negative residuals are way more than the positive residuals, so they are not randomly distributed around the value 0. The fourth one also shows you some trend, right? You can see a very obvious trends when the factor t increases. That means the residuals are controlled by some external factor t. They are not independently distributed around the value 0. These are some examples of problematic residual plots. If you get a model and then your residual plot shows the problems to you, what should you do? You cannot use the model from the sample to predict the population, because that means your data set in the sample are controlled by some external factors. Ideally, the residual plot of your linear model should look like the one on this slide. If you cannot get the residual plot like this one, then you have to consider drawing a sample again and then use the new data to predict the population. This is the third factor you need to check, the residual plot. Residuals should be randomly and independently distributed around the value 0. Now let's take a brief review about what we have learned so far. If you believe one factor can influence another factor, and then you draw a sample from the population. You predict the values of b sub 0 and b sub 1. The software will give you an equation. That equation is called a linear regression model. So once we get the linear regression model from the sample, we can predict if the population has a similar relationship. Before that, we want to check the overall regression relationship. We want to check the individual parameters, and we also want to take a look at the residual plot. We want to make sure that the model from the sample is representative of the population. In our fitness mobile app example, we only investigated the relationship between the users' yearly incomes and how long they will spend on our mobile app every week. In our model, we only have one independent variable, the user's yearly income. If you only have one independent factor, then the model is called a simple linear regression model. If in your model you have two or several independent variables, then the model will be called the multiple linear regression model. In eCollege, I showed you an example how to perform the multiple linear regression model. Basically, the steps of multiple linear regression model is as same as the simple linear regression model. Please take a look at the example in eCollege. This concludes this lecture. I will see you soon in the next one.